Yes, I'm sorry. I was talking to myself. So welcome to everyone to this session that is dedicated to introduction to time series modeling. And normally we will be together for at least an hour, let's say. And we are just waiting few minutes before starting. And we'll be talking about, like I said, time series. It's a rather introduction level. So if you are familiar with advanced technique such as, I don't know, Sari max, moving average, etc., we won't go into too much detail during this session. This session is intended for really people that just start the subject. But I hope that I will be able to show you a few things. So let me share my screen and maybe we will start. Share screen, and I think that's okay. I will. Okay. So welcome to those that joining us. And like I was saying, the main subject of this session will be we will talk about time series modeling. So exactly what it is, what kind of modeling can we perform with that? Do you have any idea on how much time this live will be? Normally, we will be together for let's say for an hour, 45 minutes, and normally it should be good. So I will try. Maybe I will start now. If you are, maybe I will start just now. So just let's go. Let's go. Hello, everyone. Okay. The content of this session. So first of all, I will introduce myself to tell you a bit about myself. We will be talking about time series fundamentals. So the basic idea. So what it is actually what are we searching for when we are working with time series? What kind of modeling can we do with it? And we will try to show you a global strategy. That's the point three. The strategy is how do we do when we want to perform a time series modeling. After that, I will share with you some modeling basic step. Is the first step that I encourage you to try when you start working with time series. And we will just have a kind of a peek into the deep learning way of modeling, but it's just an introduction. So you will see just rapidly how can we do it using deep learning, and maybe for another session we will go into more details about deep learning or other modeling approaches. So a word about myself. I'm Sébastien Simé. I'm a data scientist and a data engineer here at Decomposition Test. I'm very thrilled to be with you today. And I'm part of the pedagogical team at Data Test. So here at Data Test, we talk a lot about data, but about how to use AI technology, generally speaking. And I'm very passionate about AI in general. That's why I joined Data Scientist. And on a daily basis, I will navigate between machine learning, deep learning, data engineering, technology, and cloud technology as well. When I'm not hard work, I'm a writer on my own, so I try to write, of course, on AI and on other subjects as well. The requirement for this session normally is a rather introduction level, so you are not supposed to be used to this modeling. So if you have no prior experience, or if you have just a little experience with time series data, this session is for you. If you are used to work with time series and used to model using different modeling, maybe you will find it a little bit boring, but you can learn some few things from some tips from here. So stick with us, and we will discover it in a minute. The main objectives of this session, what I want you to remember at the end of the session is exactly to understand what time series are. So what it is, I'll give a good definition to this notion, give some application. How do we use time series and what type of analysis do we perform with that? I will share with you general modeling tips when you start the modeling task. So when you want, for example, to forecast some things, few things, we will talk about it in details. How should you start your journey into the modeling of using time series? And as I said before, the focus will be on the very basic steps. So no deep talk about really advanced techniques, but I want you to understand the very basic about time series and how do we start an analysis when we are working with time series. So let's start with the fundamentals of this type of analysis. So we will talk about the data source. Where do we find time series, generally speaking? Time series is literally everywhere you can think of. If you think about your heartbeat, if you want to measure the temperature, if you want to follow the stock prices, if you want to study a signal, a sound wave, these are a few examples of time series actually. So with unstructured data, time series data are among the more present in a daily basis. So we have a lot of record that we can have with IoT devices, connected device, etc. So time series is literally everywhere. So it's very important, first of all, to understand what it is and what to do with it. So next question is, what exactly time series? So time series is a sequence of data point dependent on time. So we have this is the value that is associated with a timestamp. It's like you want to study an experiment. You will measure, you will get some measurement that you will link to time, and when you will have the global data set, it will be a time series sequence. So that means that each data point, like I was saying, is assigned to a timestamp. The sequence is ordered, of course, since the times doesn't we doesn't normally we don't created the technology to go back in time. So normally the sequence is forward and ordered. So we have a ordered sequence of numerical value, usually equally spaced over time. So the frequency at which we get a measure will be the same during the whole experiment most of the time. If a single value at each timestamp, if we have a single numerical value at each associated to each timestamp, we will be talking about a univariate time series. That means that we are just tracking a measure of a single measure over time. But if when we have more than one value associated to one at each timestamp, we will be in the case of multivariate time series. So that's the you will find both data set on internet. You will find most of the time you will find univariate time series. That means that you are only recording and following a single value, but but you will find a data set with multiple value associated to a particular timestamp. That means that we are working with a multivariate time series. So as an example, this is what it should look like generally when you are just tracking a single numerical value. You can see some patterns, and we have the date on the x-axis. We have the timestamp here, and we have the numerical value here. So we can follow the evolution of the parameter that we are studying over the time. This is the representation, a graphical representation of the data, and the data itself Normally is available in a CSV file. Normally, most of the time, we have a timestamp and the value associated to each timestamp. For multivariate time series, this is the example that I can share with you. If we are tracking at the same time the latitude and the longitude of a car, for example, at each timestamp we will get both numerical value. So we will be tracking different value. So we are in a multivariate time series. Some application of a time series. Of course, the first thing that you will do when you will get into when you will have access to time series is what I call the exploratory data analysis. Is the same as using usual data with time series. You will kind of plot some graph to understand to draw some insights using your data. So the first type of application is to understand what it is. So to understand with a graphical way, we will be doing that using plotting function like those we are seeing to understand the general pattern in our data set. Other application is for predicting the future. That is the most point of using time series. So generally, we are interested in predicting what will happen. So we are talking about when we want to predict the future, we are talking about the forecast. We want to forecast the value at a given date in the future. And of course, we will be recording the value, the true value, continuously. So we will be able to compare our forecast with the true value once we get the true value. You can find also, excuse me, you can find also you will be interested on doing what we call imputation. So this is the graph on the middle. You have a time series, but you have some missing data. So a task that you will see on internet is how do we fill the gap that we are seeing here. So we will use also maybe time series modeling or other very basic operation to fill the gap, to reconstruct, to build the whole evolution of the experiment that we are tracking. So we have time exploratory data analysis. That means using graph to understand the data. We have when we want to predict the future, we want to forecast, or we want to fill the gap. So we are talking about imputation. And of course, we can use time series to for anomaly detection. And this is a concrete and a real application. For example, if you work on the cloud, and on the cloud have some services that track the interaction of users with some services, and some model are constantly scanning the traffic to detect if a traffic is unusual or is very normal. So we are talking about anomaly detection. The same analysis could be performed using your credit card to make sure that it's you that you are actually that is actually using your credit card. So we are talking about anomaly detection. When we are working with time series, we have what we call the components. It's very important that we understand um, the component of a time series is a way of decomposing the time series in on very simple signal to understand more what it is. So you have three main components that are usually studied when we are working with a time series. Let me just read the question. What's the best way to impute data? This is a good question. Like in a forecast, for the forecast, in a forecast task. So when we want to predict the future, there is no really a good way of modeling the future. So for the imputation, it's the same thing. There is no really a good way to do an imputation. Of course, we can create some model to fill the gap on the period that we are missing data on, or we can use simple technique like, I don't know, take the previous value or take the means to fill the gap. There is no really good way of doing so, and we will try just an approach, and we will see in the reality how it perform, and we will move on from there. So that was for the question. So coming back to the time series component. So any time series, I'm talking about any time series, have mainly three components. If we decompose this series in very simple signals, we can decompose it using these three components. The first component is what we call the trend. So the trend is here at the left, on the graph on the left. We have a upward trend on this time series. So the trend is a upward or a downward change in the average value. So we are tracking. We want to see the evolution of the average value of the time series, and this evolution could be seen using the trend. So when we have a time series, we will in practice extract the trend to see the evolution of the average value. And we have the seasonality as well, which is another component. The seasonality is the periodic change that follow an identifiable pattern. Here we have at the middle we have a seasonal pattern. You can see that we have a form that repeats itself over time. So that is the pattern that we want to identify clearly, and in practice we will make sure to separate the trend and the seasonality, to study them separately, even if both are included in the same time series. So the first thing that we will do is to decompose the time series into its major components to study the patterns of the seasonality, for example. And on the seasonality, what we are interested in is the peaks and the space between the peaks, to make sure that we keep some purposes that we will be talking about later. So we have the trend, we have the seasonality, and of course the last component is the residual. What is called the residual, or the noise, is the random fluctuation that doesn't follow any patterns. So in any signal, in any true signal, you always have some level of noise that you want to separate from the trend and the seasonality, to clearly see the evolution and the structure that repeats itself. Um, uh, I'm looking. Take me. It will be one that are the previous. Okay, it was a comment into the chat. So let's continue. So we have the component, three main component: the trend, the seasonality, and the noise. So when we have a time series, first thing we will do is to decompose, to study them separately, and to study some properties. The next question is, how do we do it? How do we decompose a true signal into its component? So in Python, it's very simple actually. You simply have to use the seasonal decompose. This is a function that you will use most of the time from stat module, and you will simply use this function directly on the series, and as an output you will get the trend separately from the seasonality and the residual. So you will be able to clearly see what's going on inside your data. uh, in reality, the true signal are in reality they are it's a mix of everything, I would say. True signal won't is very unusual to have a time series with only trend or only seasonality. You will always get some combination of all the patterns, and That's why I'm saying that the real-time series could be a combination of the will be. It's not could be. It will be the combination of a previous component. As a combination, you could have an additive combination. So that means that you just sum all the components together to form a true signal. Or you have the multiplicative time series, which is a multiplication of all the components. So here we are. When I'm writing this kind of equation here, is I'm already a bit doing modeling. So when I'm looking at the time series, I will try to kind of just by looking at the graph, understanding if the different components are summing up to form the global series, or we have a multiplication here. So depending on the time series and the pattern that you observe, you will be rather additive or multiplicative or a mix of both. So real time series is a combination of all the components that we previously saw. So for the first graph at the left, here we simply have the trend plus the seasonality. So we can see the upward trend and the kind of a structure that repeats. And here, but here you can see that we don't fluctuate any not very much. That means that the observation are very easy to see, but in reality you will have some noise that will just create some randomness inside our data. Another thing that is very important when we are talking about time series is the time series stationarity. Um, the idea is that if the future is similar to the past, it is easier to predict what will happen. So most of the time we are comfortable we are comfortable working with a time series that is stationary. What is the meaning of stationary? There is no good definition as the mathematical one. Mathematically speaking, a time series is stationary when its statistically purposes do not depend on time. That means that the means, the variance, and the covariance of the time series doesn't change at all the time. So if you have a series that is very have a constant mean, a constant variance, and a constant covariance, you will be able to predict what will happen more easily because the pattern we can clearly see that the evolution doesn't change at all. So it's easy to say that following this trend, this is what we will get at next point in the time. The challenge will come when your time series is not stationary. And we have the above this picture, the first graph that show some different case that you can have. You have the first case when the mean is dependent on time. You can see that the mean value are changing over time. You can have the variance inside your signal that change over time, so you will see some increase or decrease of in the magnitude of the wave, I will say. And you have the covariance, and so I was talking about later to the distance between peaks. And if you see the distance between peaks that just change over time, that's an indication that the covariance is shifting. So we are talking about our statistically, yes, statistical. Thank you. I will correct it right away. Let me just up statistical property. Thank you very much. Okay. So it's very important. It's a very important characteristic of time series because sometimes models perform better when the data is stationary. So when your data have a constant mean, a constant variance, and a constant covariance, the model will predict without much problem. But when you will, like often, when you will have a true value with some properties that are not constant, it will be challenging. We will see that it will be challenging get to the point when we are comfortable with the prediction. Time series stationarity. When the time series is not stationary, we will in practice transform the letter using differencing method. That means that when we when if we provide you some time series that is not are not stationary, the first task that we will do most often is to apply some transformation to get back to the point where to end up with a time series that is stationary in order to apply model on it. So here we have an example. We have this example. We have this time series which is clearly not stationary, and we will apply what is called a differencing method. So that means basically we will subtract the value between two timestamp, and we will end up with this type of signal which look much more like a random signal. And with that, we will be able to use model that will perform very that will be better at prediction. Of course, in the reality, um, after this transformation that we will apply to our data set, in order to make sure that the different time series is stationary, we will use a statistical test to make sure that this is indeed a stationary time series. So the statistical test is called the Decomposition one. So the methodology is that you have a time series that is not stationary. So you have a time series, you apply the Decomposition statistical test to see clearly if the series is stationary or not. If it is the case, that's okay, you continue. If it's not the case, you will move on and apply a differencing, the differencing, and this operation will transform your signal into a signal that look like this. And on that, you will once again apply the Dickey-Fuller statistical test to make sure that it is stationary, and you will continue until you get to the point that the signal you can use it for modeling. Yes, I'm looking at in the chat different methods. Yes, I'm talking about the different method and the second order differencing. So sometimes we will just perform once a single difference, and we will end up with a signal like this. And sometimes we will have to difference more. So it will depend on the data that you are working on. So once we get there, so we have a time series, we have the application. We now know what it is, what we can do with it, what we have to start doing it. So when we have a time series, you will start by analyzing a bit, decomposing the time series, analyzing the different components separately. Of course, use the statistical Dickey-Fuller test to make sure that your signal is stationary, and obviously after that you will move on to the modeling step. So in this presentation, I will talk about the forecast task. I won't talk about the imputation task. The imputation is to fill the gap that we identify. The methodology that I will present is similar, but I choose to have a focus on the forecast. On the forecast. So let's say we are working on the forecast. Time series forecasting can be approached with a wide variety of models. Only to model a single time series, you can apply numerous techniques, from machine learning to deep learning, and using statistical model. You have a lot of model that you can try. I'm looking into the question into the chat. I have a question. Why should we decompose the data if we will have to test if the data is stationary? Because how can I say this? Why should we decompose the data? The decomposition task is It's for you. It's for when you are starting with this time series. You want to separate what is seasonal, what is the trend. That is the purpose of the decomposition. So you will do it for for exploration, to make sure that you are not hiding something, to understand a bit what is inside your data. You will decompose because it's more easier to see trend separately from the seasonality and from the noise. Generally, you will do this for exploration. It's not a mandatory step. Yeah, there is other ways of doing such exploration, but you will see in the literature that most of the time, at the beginning, we decompose, we observe a bit, and when we see we move on from there. Let me see another question. Exactly. So it's not part of the model. No, it's not. It will help you to model, because if you understand your seasonal pattern, that this information will help you in the modeling step. So you need to decompose to separately observe things, take notes about some properties that you will observe and use it for the modeling. So I was talking about modeling. The modeling, we can do it on a different. We have we have numerous algorithms that you can try to model time series. The general strategy when you start working with a time series, you will start by analyzing, as I was saying, the components, to understand to see what is the trend. Do I have a constant mean? Do I have a constant variance? Do I have a constant covariance? And you will see that on the raw data, the raw value, so the signal, the true signal, and you will see that while you decompose as well. You will observe both diagram and decide, understand, and draw some insight about that. So normally you start by decomposing the signal to study the signal in details. Of course, you could also plot the histogram of the time series value. That will help you, for example, see if you need to apply a transformation, let's say a logarithm transformation or a power transformation, in order to have your histogram look more like a Gaussian. So this is another way of analyzing the data, the raw data. I'm looking at the chat. If the time series is stationary, did we still have to use the decay Fuller test? Yes, you have to use the decay Fuller test. It's an insurance. You want to make sure you just don't want to look at the graph and say, okay, that look nice. You want a proof of what you are telling. So the proof of everything in machine learning in general is to use a statistical test that will just allow you to have the right to say that, to have the right to say that it's okay to move on. It's a good habit. I won't say that you don't have to do it. I will always say that you have to do it, even for yourself, to make sure that, of course, it is stationary. It's not the only thing that you can do to make sure of it, but the decay Fuller test, if you look in the literature, you will find that um, some author iteratively different and test using the decay Fuller until they reach a signal which is stationary before moving on. Okay, so first, the global strategy is, first you start by decomposing your series into its component to study and to understand what it is, what is the period, what is the frequency, what is the trend. And already like this, you can draw some insight and talk with the manager or the sales and say, okay, we can see that and we can see that. So the first task is exploration. Secondly, when we are getting into the forecasting, so the modeling step, the next step will be to split the data. So you will split the data to have a part of your data on which you will train, and as usual, in another part where you test or you validate your model. And third, after splitting your data, you will generally start the forecasting task. with a very basic model as a baseline. This is very important. I should put it in bold. When you start modeling using time series, start very with a simple model before going into other stuff. Because if you start with something which is rather complicated at first, let's say you start with a, I don't know, Sarimax model, you will work a lot on finding the right parameters, and maybe if that's okay, that's good, but the risk is that you get lost in too much details. The first thing that you want to do is try a very simple model and to see how it perform and move on from there. So if you reading to the chat, if you know if the time series is stationary, you don't need to test, but you cannot know if the data are stationary or not before testing. You have the Kefler. Yes, so that's what I was. Thank you for that. So if a little recap, you start by exploring, understanding your time series, understanding the purposes of your time series. After that, you move on, you split your data, and you start the modeling task with a very simple model. When to split the data, of course, you don't split the data like in a normal machine learning, because in a normal machine learning, you will use the train test split of scikit-learn that will shuffle the data, etc. So in time series, you do not want to shuffle the data. So you have to pay attention to just split without shuffling. So you just split the data. Most of the time, we use what we call the fixed partitioning strategy. That means that we will, for example, split the data into three parts: the training, the validation, and the test. That is if we have lots of data and we can afford to do this. If we don't have a lot of data, we can split into training and stop with the training and validation. So we will train on the training set and test or validate with the validation if we don't have enough data. So when you have a lot of data, you will most of the time divide the data into three. You will train on the train, you will validate and do some fine tuning with the validation data set, and then you will use the test at the final stage. I'm looking at the question. We can use train to split of scikit-learn by putting the yes. You can use the shuffle equal false to not etc. To not shuffle the data. So okay, that thank you. You can do this. It will work. You will split without shuffling. So you just have to make sure that you don't shuffle. So talking about splitting the data, so the general strategy is used the fixed partitioning strategy. When you split the data, another point that is very important is that you have to include a whole number of periods. Let's say that on your data set you identified, for example, that the period, the amount of time on which you have the same pattern. Let's say that on the period is a year, for example. Let's say it's a year. So you will divide. You won't cut a year in half. You will include in separate splits a whole number of period. You don't want in 1 year to be at the same time in the training and in the validation. You split, including a whole number of periods. Another strategy that is not very usual, but that is more natural, I would say, is to use what we call the roll forward strategy. Like that we have on the graph. In this splitting strategy, we progressively increase the size of the training set to mimic the data evolution, because you know that when let's say you have a model in production, you will have to retrain your model on a constant basis in order for your model to keep its performance. So to take this mechanism in account during the training step, you will practice the roll forward strategy. That means that you will start with a size of the training, and you will progressively increase the size and decrease the size, of course, of the validation several times to to mimic the real evolution of your data during in real life, because in real life you will retrain on a constant basis. This is not very usual, but you can find it in the literature as well. Um, so now, if we talk about the global training workflow, so we perform an exploration, we split the data, and now we are ready to enter the training workflow. To validate the performance, the performance is using the fixed patch. So we are putting ourselves in the hypothesis. We are using a fixed partitioning strategy, and we want to forecast. We want to create a model that will forecast the future. That means that we will start by training on the training set, of course. That is obvious. We will evaluate the model on the validation set, which is very classic. We will iterate on one or two. That means training on the training and evaluate on the validation to evaluate the different model and tune the parameters that so that we make sure that we have parameters that perform the best way possible. Once we have reached a good the parameters that are really good in terms of performance on our model, we will train the best model with the best parameters on the training plus the validation set, and evaluate the best model on the test set to see how the model will perform in real life. This is the purpose of the fourth point. And of course, before deploying our model in production, we will train the model, the final model, on on the whole data set, so that we will put in production a model that have seen all the data that we have and is ready to forecast the future. So it's very progressive, as you can see. Um, so we perform an exploratory. We split our data using the fixed partitioning strategy. You can use the roll forward, but most of the time you will use the fixed partitioning strategy. You will progressively find the best parameters, evaluate the performance, and train on the whole data set. And uh, so to do so in a good way, what is recommended is to, as I was saying, start with a very simple model. So you don't want to just start with a very complicated model. So the first approach that we will do is to use what we call the naive approach. The naive approach is the base model that I recommend you to use at the beginning. So you use the naive approach as a modeling baseline. The baseline of the model, the naive approach consists in taking at each time step the previous value to forecast. It's very simple. It's at a given time, you just take the previous value as the forecast, and you do it for the whole data set. This is the naive approach. It's very simple, and in reality, you will find that this approach is very difficult to challenge. It's very difficult. Most of the time, you will stop there, because the naive approach sometime will answer the question better than any model that we can try. So, naive approach, you simply use the previous value to forecast the future. That's it. And this is the graph. I can say when we plot it, you can see a kind of a shift between the true time series and the predicted one. We have a little shift, and we can see that most of the time we are following all the changes with a little shift. Another approach, after applying the naive approach, if that's not okay, if you find that this is not enough for you, you can move on to the moving average approach. What is the average approach? It consists in taking the mean of past value on a given windows. Let's say we have a data set that we have on the left here, and we want to to average these three value. We will take these three value, we will average them, and we will use it as a forecast. Simply, we are considering values inside a windows, and we average the value, and that's it. So, in the moving average approach, you have it could be you could use a centered windows. That means that the windows is centered, or you can use a one-sided windows. That means it's the position is simply the position on the value and the position of the windows on the data that you want to average. So, like, as a recap, first, in naive approach, you simply take the previous value. Second, moving average approach, you simply consider the value inside a window, and you average the value and you use it as a prediction. And to do so, you can use either the centered windows or the one-sided windows. But you could find that this moving average, like on the example that I show here, the orange line is the prediction simply using the moving average, the one side the one-sided moving average. And you can see that sometime this forecast will fail to anticipate trend and seasonality. We can see that when we miss, we don't we did the model didn't predict at the same time that there is a rise here. The prediction is kind of we miss few things that are very important. So this is the effect that you could observe when you are using the moving average. You could have it. You can observe this thing that you have a true signal, and when you average, of course, you can see that generally speaking, you follow the evolution. But what you want, for example, in your business case, is to detect changes, rapid changes as soon as it appears. So with moving average, you could have some delay. So what like the next question is, what can we do when we have this? So the next steps after the moving average approach is to, as said this before, apply the difference method. We will difference our true value. This is it. So instead of you considering the raw value, we will simply difference. The difference is equal here to we take the value at the time step, and we just simply subtract the value at the previous time step. Of course, we will use the period, a period that we will that we have found using the decomposition step here, to make sure that we end up with a signal that looks more like a random noise. So when we fail with a moving average to anticipate rapid changes, generally speaking, the next step is to include some level of differencing. That means we take the raw data, we apply a difference method, and we end up with a signal like this. And of course, we can apply a moving average on the different time series to forecast. So the red line here is the moving average of the difference time series, which is in blue here. To get back to come back at the true prediction, we will this method requires some level of transformation, because we need to get back to the true signal here. So with a difference time series, we will apply some transformation to reconstruct the true signal. And as you can see here, the true signal, which is the true signal, is in blue. The predicted one using the difference technique is in orange here. Let me just go inside a notebook that I prepared to show you a bit all this in action. So rapidly to introduce this notebook, I've created a fake time series. I've simply use a linear trend with some seasonality and with some noise that are summed to have a signal that look like this. I started decomposing my signal, and first naive approach, as I was saying, I simply take the previous value. So this is the prediction, and you can recognize here the picture that was on my slides. So I simply take the previous value, and that's it. Next step, moving average. So moving average, I've applied the differencing technique, the difference technique on the raw data set. And you can see the graph here, we fail to anticipate things. And when we fail to anticipate the trend and the seasonality, this is an indication to apply some transformation. So next transformation, some next transformation, applying some difference technique. It's very easy to do it with pandas. As you can see, you simply use the diff method to difference a time series. Of course, you have to find the good period, but if you find the good period, you will end up with a signal that is difference and stationary. So this signal, I didn't use the decay Fuller test here, but believe me, this signal is stationary. So on the difference time series, I simply um, uh, compute the moving average on the difference time series to end up with the orange line here. And to get back to the true signal, I add back what I subtracted earlier to come back here. So if I show you the pandas code, I simply this was the value that I subtracted when I was performing differencing. So to rebuild everything, I just add back what I subtract. This is simply what I saw. What if you don't have any specific period? If for the period, that's why you need to decompose at the beginning. When you have a true signal at the beginning and you don't know the period, this is the thing that you have to find for yourself. So you will compare the global range of your data set. For example, here, if I, here I've used, for example, I suppose that um, I have about 4 years of data. So I have a number of rows. That is my basic unit is the day. I imagine that I have a measure every day on 4 years. So I simply divided the number of line that I had on the number of years of data, and I found the period. So I used this period in my data set. So to answer the question properly, when you will start with a true time series, the first question that you will ask yourself is what is the period of your data set? And to do so, you will do some exploratory analysis. You will look at the range of the data. You will look at the amount of data. And normally, when you decompose and when you compare everything, you're supposed to find the period, and that's the thing that you can use. You can use to difference. Another approach is to simply, I don't know, write a for loop, for example, and iterate, and until you end up with something that is okay for you. It's a brute approach, but you can try it. Okay, so I just can show you rapidly. So here I compute the moving average on the different time series, and after that I simply took this value and I add what I subtracted earlier during the differencing above to reconstruct the true forecast, and then I superimpose both graph on the same graph. But when we are looking at this, we can say that it's good. It's actually good because we don't we can see we can anticipate things. We can see when the data are raising and when it's a fall. But the forecast is very noisy. because you can see that there is a noise. There is a noise inside our forecast. Of course, you have to measure this noise by using a metric. Uh, let's say mean absolute error between the forecast and the true value to have a feeling of, is it okay to leave it like this or not? Maybe it will be enough, or maybe it won't. So you will use a metric, you will compute the metric and decide if this forecast is satisfactory enough for you. If that's not the case, that means that you have to try some other stuff. So what I've done is simply, since I have a lot of noise inside my forecast, I simply once again applied a moving average on the forecast, and I end up with the line here, which is less noisy and perform a little bit better than this one. Let me look at the question. Shift up in the future, or shift up in the future a bit. I don't understand the question, Thomas. If you can rephrase it, maybe it will help. But I'm looking at the chat, the time that you can, and I continue if I don't understand really the question. So if I recap, the value predicted is higher. Yes, you can see that we have some at the end of it. Exactly. You can see that we have a. It's not perfect. Of course, this model is not perfect. It's simply a model, and we can see some we capture the trend. I will say the evolution much better, but the noise is very confusing. That's why I applied a moving average on the forecast. And once I do that, I have this line which is a little bit smooth and perform a little bit better. But it's not. It could not be enough. But in reality, you could find that it's very difficult, because since then I didn't use any machine learning or deep learning since the beginning. I simply use the data as is, perform some transformation, some differencing, some moving average here and there, and just by using it, you can end up with a prediction that is very, very interesting to use. One precision: does your model learn the signal or predict the signal? This is a good question, actually. I would say that a little bit both. Why I'm saying this, I'm using the data as is, of course, with some transformation uh, to predict. So we can say that I'm using the data as is, of course, but I'm applying some transformation, and this transformation is supposed to help me understand what will happen. It's not saying that it will be perfect. It will help me have a feeling of what can I expect if I simply use this value, combine some perform just some transformation. What will happen if I just do that? This is the question at the beginning. So with this question at the beginning, without any deep learning, any machine learning, any Sarimax, any Sarima, any Arima, etc., I'm just using transformation. And for example, with the orange line here, my orange line will be like my forecast. I can see that I don't have all the peak and valley, etc., but I can predict pretty much the mean value of my observation. So it's not bad. It's more predicting the signal based on the past. Yes, exactly. It's a mix. It's a mix. But I recommend doing it as a first approach before go deep dive into the modeling with other parameters. You simply use the data and you move on from there. So that's why I was talking about. So until here, I simply use the data. First of all, I use the only the previous value. It was not okay. I used the moving average. It was not okay. I applied a the difference method, and I rebuild a signal. It was not okay, and I simply applied the moving average on the forecast. And it's not bad, but it's not perfect. It's not perfect. But until there, with this model, I have a solid base model, because the purpose after that will be, can I find a machine learning or a deep learning that will perform better than this? And this is a real question. So this is what I want you to remember, is that before using some advanced technique, think about just with time series, use a simple method, and most of the time you will find that it will be very much difficult to beat basic techniques like this. So we were talking about machine learning. So for the machine learning step, if I go rapidly, for those we are in a hurry, after just simply transformation, we can enter the realm of machine learning, because my purpose before was to get to the point where I have a solid base model, with a good prediction power, and then I can move on using machine learning or deep learning to see how it compete. I'm looking at the question and this prediction. Yes, no, uh, and this prediction can predict the future. Then how far? And yes, you have a good question. I didn't show you in the slide, but actually each time that I'm creating a forecast, I'm computing the mean absolute error, and I'm comparing the mean absolute error with all the approaches I use. So I started with the naive approach. This was my error. I used the moving average approach. It was worse. I used a difference technique. It was not bad, but we can do better. And by applying a moving average on the last forecast, I was able to be better than the first naive approach. So I use the mean absolute error, but you have different other metrics that you can use. Looking at the question, we cannot say how far, but the more you go forward, the less model will be efficient. Depends on the situation, the model really. No, no. Some model will be. I think from some model could be very efficient. It's simply that my main purpose is that uh, when you will be facing time series, before actually starting something very fancy, think about starting very with simply simple methods and see how it perform, and then after that you will move on to the machine learning step. So for the machine learning step, the tricky thing is, if you want to use the machine learning on time series, you have to transform a bit your data set. You cannot use it right away. To do so, I have this example here. I suppose that this is the time series. This is a numerical value that are time stamped. So we will use some technique, some algorithm, let's say this, to build this data set. And on this data set, you can see that we will use, for example, the four first value, so 0, 1, 2, 3 as the features, and we want to predict the last row, the last column, so the four here. So we have to kind of rearrange this series into this data set, and with this data set you can apply any machine learning at all. You can apply machine learning. The tricky thing is that you have to perform this transformation, and looking at the signal itself, that means that we will use the value of previous timestamp to predict a next timestamp. This is the ID. So we will use, we know that in the past we have 0, 1, and 0, 1, 2, and 3, and we want to predict the 4. And when we will have 1, 2, 3, and 4, we want to predict 5, etc., and so forth. I have more feeling that it's a good modelization of the signal, like a simplified version of the signal. It's a it's a simplified version. But what do you call a model? A model is what will represent on a more general way your data set. So every time that you will use some technique that will get you to a point where you have something that you can use as a generalization, this is a modeling. So this is a simplified version, but literally speaking, a model could be a simplified version of your data set, because you give the data and your model are supposed to learn from the data and generalize. So that's the idea. Okay, let's wrap it up, because I think that most of you will be. We have other things to do. I will simply rapidly show you what can we do in the machine learning step. Of course, you are free to use any machine learning once your data set is like this. So you have a data set with previous value, and we want to predict the last columns. You can use random forest, etc. What you want. What I tried is to use a linear model, using some function of TensorFlow. So to create my data set, I have this function that will take a series and output a data set with this form. So the previous value like this and the target value. So this is the sole purpose of this function. And with this function, I simply show you how we will look like in the training step. So I use it on the range of 10, and you can see that we have the feature that is 0, 1, 2, and 3, and we have the target, etc. Associated to that. I've this function produce batches of data because I want to use a bit of TensorFlow function. That's why I wrote this function. But you can use any other algorithm. First thing that I did is since I wanted to use TensorFlow function, I wanted to try to find the right learning rate to use. So I use a bit. I use maybe you're not familiar with it, so I won't get into too much detail. But I use what is called a callback to train a model using a simple neural network with only one neuron and without activation function. So this is a linear model. It's simply a linear combination of the inputs when you are using it like this without activation function. It's like you use a very basic model, actually. But I wanted to make sure that I use the proper learning rate, because deep learning models are very sensitive to that. So I perform some exploration of the learning rate before I will pass it very rapidly, just to make you see that with it's a very linear model. So this is simply a linear combination of the inputs with simply a linear model. I could not yet, if I just show you the error here, I could not compete with simply using differencing and moving average. So simply using a linear combination of previous value and trying to compute the next value in the next timestamp. I could not do it. And as a challenge, you can try. You can try. Since I followed this experiment until the end, to beat actually this value, I had to use very complicated model in order to beat this error. So I had to complete to use not only a deep learning, not only dense neural network, but other stuff as well, in order to have a prediction that is not far from that. That's why I wanted to show you something very simple, show you something that is a little bit complicated, and make you see that it's not because you use very complicated model at first that you will end up with high performance. You have to think about it very no. Okay. So other modeling options, of course, here I simply tried a linear combination of the inputs, but you have, of course, the autoregressive, the moving average, the autoregressive integrated moving average, etc., etc. Is statistical model that you can use to predict, of course. You can use the dense neural network. I simply use one dense layer, but you can stack several dense layers with activation function and try it. You can do it. You can use RNN, recurrent neural network, because we have a sequence. So you can use RNN, but I can tell you that with the data that I just created, even RNN wasn't enough to beat the very simple method. And of course, as a last resort, you could use the one-dimensional convolutional neural network as well. So with time series, you can do all the modeling. Uh, you can try all the models that exist. Actually, you have statistical models. I'm talking about Sarima, Sarimax, etc. You can use neural network. You can use classic models. You can use every model that you can think of. So as a recap, time series could be used in numerous industries. You will find it in insurance. You will find it in physics. You will find it everywhere. Literally, anytime that you walk in the street, you can generate data that could be used time series. In time series data, each value is associated to a timestamp. So with the time, we associate a value and we track the different value over time. Different type of analysis could be performed. So you can simply use exploratory data analysis on time series to understand the trend, the seasonality, and stop there. Or you can do some more advanced tasks like modeling and creating model. The first task, when my main point during this presentation was to say that before using anything advanced, always consider using something that are very simple to use and create a very solid base model before starting your journey into the modeling, because this way you will find that you will develop a good feeling about your data. You will understand very deeply what you are doing when you are using very basic things. So always, if you should remember one thing when you work with time series, always start with the naive forecast. It's the very basic model that you could use. You will find it in the literature. It's the very basic model that everyone start at the very beginning. Of course, after that, um, depending on the author, you will find some of them that will move on to the moving average, etc. Or you will find other that will jump right into the modeling with using machine learning. But the first step is the naive approach. So that was it about this session. I didn't show you everything in the notebook, but if you are a data scientist and if you are interested, I can give it into the link so that you can have the code and review it on your way. And if you have any question, you can write it into the chat. And normally, this is the end of this presentation. So if you have question, I hope that uh, it answered some of your questions that you had on regarding time series. So I'm open to question if you have any into the chat. Or everything is very clear. So I hope that everything is very clear. Before you maybe you think about some questions. Um, The next event like this will be with one of my colleagues. We will talk about a subject in deep learning. You see, it will be introduction to deep learning very soon. So stay tuned to our channel. If this session was helpful to you, don't hesitate to thumbs up and subscribe to the channel. I hope that I answered some of your questions. That it was very interesting. Oh, some question. Can we have the slide? Of course, I can share it. I can share it to you. No problem. I will see how to include it into the comment or else. Arima, Sarima, SVN, RNN. Can you rephrase, Thomas, for me, please? What about storing time series? Storing time series. Deep learning model will be checked. Okay, let me just. Can we have the code? The code as well. You will have the code, of course. The slide, yes. Thomas, can you please rephrase the first question? Arima, Sarima, SVN, or RNN? You are asking how to choose between this model, for example? I don't know. Deep learning model will be seen in next video. Yes, you will talk about an introduction to deep learning. I'm not sure that you will see everything, but you will see some introduction about the very maybe the foundation on deep learning, what is a neuron, what is a layer, etc., and stuff like this. Those deep learning model will be presented, or the deep learning that I just shared here. I'm not sure that you will see everything, but I don't know if you follow one of our training at data scientist. In the data scientist track, we have all these technology that are available. So we are training using all these techniques, of course. And we have some blogs on it as well, if you are interested. Okay. VH, what about storing time series? Could you rephrase also? You will be storing, how storing? I don't understand. I'm in data engineering right now. Okay, if you are in data engineering, you could ask to your cohort leader, for example, if you could have some module on deep learning to learn about it. What are the best way to store time series? What is the best way to store time series? This is a rather data engineering question. I don't know how to answer that. You have different technology that you can use. The very simple way of storing time series is like you will find on the literature is inside CSV file. You simply have a file with one column with the timestamp and the other column is the value. This is the simple storing object that you could have. But if you want to do something more advanced than it, you have databases that are more appropriated, but it's other subject, other topic. But the very simple thing is CSV file, uh, and you will store it like this. Okay. I hope if you have any other question, I'm still here. If that's clear for you, I hope that it was the case. Don't hesitate to share your thoughts about this. And if you are interested, you have, like I was saying, a few other subjects that are just coming. So stay tuned. And thank you, all of you, for your time and for your question. It was very pleasant to exchange with you. I hope that I will be. I will, if you very like this one, I will create another session like this, and I will focus more on, for example, using statistical model, because I know that is very interesting as well, because we have some techniques that you could use to find the best parameters when using autoregressive, moving average, etc. It's another subject. If you like this one, I will think about create a session about this, and I could also think about show you how to do convolution neural network. It's not usual, but excuse me, you could find it. It could be interesting to show you. Okay, I'm looking at the SQLite, for example, or PostgreSQL. Yes, you can use a database like this to store time series, or NoSQL, or some NoSQL databases as well, as you want. Okay, so I will stop sharing, and I will thank you for your time, and I hope to see you soon on another webinar. And have a good day, good night now, and see you soon.